Welcome to the design of concrete structure course. So in the last lecture we have discussed about the properties of concrete. So before designing our main concrete structures we have to understand the properties of each material which is made up of our structure. So last class we have discussed the concrete properties, we have discussed in details about the characteristics properties and all, and what are the other parameters required to understand for the concrete uh, in details like flexural rigidity, creep, stress, strain, everything we have discussed. So in this lecture, we'll be more focusing on the properties of steel. So steel is a very much integral part in a concrete structure, uh, and we should give more focus to understand the properties of steel. So as I mentioned in the last video, that in a structure, there some portion will be subjected to compressive strength, some portion will be subjected to tensile stress. So concrete is a very good in taking the compressive strength. So concrete can take good amount of compressive strength, whereas concrete is very weak in taking the tensional force. So in that case, in some portion of the structure where the subjected to tension force is acting, concrete is may not be useful. It will break easily. So that's why we are using steel in that portion. Steel is a very good in taking the tension as well as in the compression. So that's why whenever location in a structure tension forces are coming, tension stresses are coming, there we use steel to take care about that load. Whereas in some portion of the structure only compressive forces are coming. So in that case we can use only concrete, because concrete is very good in tension, we saw very good in compression. We saw in the last lecture that compressive strength of a concrete, if it is a M20, then it is 20 MPa per 20 Newton per mm square, but the same concrete has a tension strength of hardly 2 MPa or 3 MPa. So that's why steel is extensively used to take care about the tensional force in a structure. So normally steels are made up of, you know it is a alloy of a iron, and the carbon content is added and ultimately the steel is formed. So in market you will find different diameters of steel bars are available, starting from 6 mm to 8 mm to 12 mm, 16 mm, like that. We can go up to 40, 50 mm diameter of steel bars are available. So steel bars are actually used to take care of the tensional members. So, like concrete, steel also has several types or grades. The four types of grades of steels are specified in the IS code. IS 456 2000. If you IS 456, it is not 2000, it is uh, yeah, IS 456 2000. In that code, you will find the different grades of steels available. Like our concrete also has M20, M30. If you see in the last lecture, we have discussed. So what are these four types of steels available? One is mild steel. Another one is high yield strength deformed bar, HYSD bar. We'll be discussing in details in the upcoming lectures, but here I am giving the four names whichever is available for grades of steel. Another is hard drawn steel wire, and last one is steel, no, structural steel, conforming the IS 2062. So these are the different four steels are actually available in market. These four grades of steels are available. So if you see, each grade of steel has to maintain this IS code. This IS code has specified this type of grade of steel, what should be the properties. Similarly, HYSD bar, that is high yield strength deformed bar, which is IS 1786. In that IS code you will find what should be the properties of HYSD bar. Similarly, for hard drawn steel wire is also in this code, you will find it out. So steel wires are actually used in the flyovers or prefabricated structure. But nowadays, mild steel bars has been progressively replaced by the HYSD bars and subsequently TMT bars. If you see any TV ad, many steel advertisement will come in a TV or in a YouTube where they will talk about HYSD bar or TMT bar. So TMT bar is nothing but thermomechanically treated bar, TMT bar, which is more stronger than compared to other conventional bars. So nowadays all bars are actually HYSD, TMT bars are used in a structure. So these are the different four grades of steel will be is used in a structure extensively. So now let's see the very important property, that is stress strain curve of a reinforcement. or basically a steel. So how the stress strain curve is measured in a steel? So if you see, this is the universal tensile testing machine, UTM we call it. So in this machine we keep our bars that are, steel bars in such a manner like that, and the tension is applied in both the directions. So both this part will go up, and similarly this part also will go down. So ultimately what will happen? The tension force is applied into this steel bar. So now basically in this experiment we are finding out what is the strength, tensile strength of a steel bar. So once you perform this experiment in a lab, we can get this type of stress strain curve. We'll get it. So the stress strain curve is the stress strain curve you will get it something like that. So gradually, basically, we are increasing the stress. So at the beginning of the experiment, what will happen? We are not applying any stress. We just fitted the concrete steel bar here. So the stress is zero, strain also zero. So there is no elongation in the bar. Now what will happen? So once gradually we'll apply the load, we'll apply the tensional force in this bar. So gradually stresses are increasing in a bar. So this bar stresses will be increasing. So this is the stress axis. So you can see the stress is increasing. So whenever stress is increasing, the material, the steel also gets elongated. That means the strain also started gaining. So whenever stress increases, strain also increases. If you see the stress strain, so this is a linear up to some certain extent. Whenever we are increasing the loads, the strain also increases. Means the bar also elongates, and basically the strain also increases. Now after certain point you will see that the stress is not increasing, whereas the strain is increasing. So if you see this portion A to B, if you see, so up to this 0 to O to A, in this portion it is linear. If you see, stress is also increasing, strain also increases. This bar, this graph is linear up to A. Now after A, still what will happen? The stress is not increasing, stress is same, but whereas the strain will increase little bit in this portion. So that point basically we call it yield point of a steel, and that strength corresponding to the stress value we call it yield strength. So this is a, we call it yield point of a steel. Means up to that point the material or the steel behave as a linear material, elastic material. After that yielding starts. Yielding means stresses are not increasing. If you see A to C in this region, stresses is constant, whereas the strain has increased, right? This is our yielding point. So A. So once yielding happened, then the stress will be constant. Then again, inside the material, what will happen is redistribution of loads will happening. Because of that, again after some times, the stress also will increase. Now again if we apply more force, the stress will again started gradually increasing, strain also increases. But in this region, if you see, the stress strain behavior is non-linear, whereas the O to A, this region was straight, if you see straight line, whereas from B, C to B in this region, these are elastic, curve in nature. So this is a non-linear path. So still the stress will increase after D. At D you will get maximum strength of a steel. Then again after, if we apply more stress, the stress is again not increasing but the strain is increasing. And after certain point when it reaches to E, means it elongated too much, now the collapse will happen, and it will make a sound and it will just break into two part. This steel bar will be breaking into two part once it reaches to this point. So this is the typical stress strain curve of a steel. If you perform a steel test in a UTM machine, you will find this type of curve. So in that one, very few things to note here. 0 to A in this region is basically elastic region, right? So stress and strain both are linear, linearly changing, and this is the elastic range. So our structure, we will construct a structure. Our structure should be lying in this lane, in this position, elastic position. So after A, basically the structure gets, or the steel gets yielded, means the inelastic behavior starts coming. So up to A point it is a linear behavior. After A, if you see the inelastic behavior, because this curve is not linear, right? And it is a curvy, non-linear. So non-linear behavior will start after the yield point. So this is the typical stress tree diagram of steel. You will get it if you perform a tensile strength of a steel. Now, see, now this is very complex in nature. You have to give, you will get A yield point, then again it will start gaining, again you will get C. C we call it second yield point. So two yield point you will get it. One is A is the first yield point, then C you will get second yield point, and then you will get ultimate strength here, and the breaking will happen. So the modulus of elasticity of steel is nothing but stress by strain. In this portion, we can find it out what is the Young's modulus or the modulus of elasticity of steel. And that value we know it is something 2 into 10 to the power 5 Newton per mm square is typically constant stress strain modulus of elasticity of any grade of steel. So now you can see there is a lot of complexity in the stress strain behavior. So, but in our IS code, Indian standard IS 456, so these two figures are actually taken from IS 456. As I mentioned, there are basically two types of steel you will get it. One is that mild steel. If you saw in the last grade, last slide, we saw there are four different grades of steel. So one is mild steel, another is that cold deformed bar, HYSD bar. So this mild steel, this is the stress strain curve of mild steel. Again, it is idealized stress strain curve because in experiment, if you do, you will get this type of stress strain curve. But again, this is a very complex. We cannot make any general statement with this type of diagram. So that's why our IS code has simplified this diagram into this diagram. If you see this after certain yield point, it is non-linear. But what IS code said after yielding point, it made into straight line. So this top portion actually they removed. They said, okay, don't consider this non-linear part. Just we can consider a straight line here. So that's what IS code has done. So they have idealized the actual stress strain curve into a simple one. So this is a simple stress strain curve of mild steel, Fe41, Fe250. So in steel, if you recall, let me just draw it here. So concrete, we denoted the grade of concrete as M20. If you see last slide we have discussed, last lecture, M25, M30. These are the different grade of concrete. You will get it in the market, or we can call make also. Okay, but in case of steel, we denote it Fe415, or we denote it another grade Fe215, or maybe Fe500 or Fe550. So these are the nomenclature for steel. For concrete, it is M20, M25, M30, M40, like that. What is M? M was actually mix, and 20 is the 20, MPa is the compressive strength, characteristics compressive strength, M20. M25 means that grade of concrete has 25 MPa compressive strength, characteristic compressive strength. Like that, these are the nomenclature of concrete. Whereas steel, we denote it Fe415. What is Fe? Fe is nothing but steel, and 415 is the yield strength, tensile strength of concrete, that is 415. Okay, so that's how similarly Fe215 or Fe250, actually not 215, actually 250 it is available in market. So the steel which the tensile strength is 250. Similarly, yield strength is 415. So this grade of concrete Fe500, the yield strength is 500 MPa, Newton per mm square. That means this yield strength we are talking about, Fy. So in market, once you go to a shop, you can tell that which grade of steel you want. You can request them, give me 415 grade of steel. That means that grade of steel has a yield strength of 415. Similarly, you can purchase 500, 550. If you see in a TV advertisement in steel, they will tell, we sell Fe550 grade of steel. That means the yield strength of that grade of steel is basically 550 Newton per mm square. Anyway, so this is the stress strain curve. You will get this diagram in our IS 456. This is basically Fe 250 grade of steel. Similarly, this diagram, if you see, this is the 415 grade of steel or higher than 250, that is high HYSD bar. This is the stress strain curve. So in HYSD bar, you won't get any clear yield point like here. Here you know that at this point is basically, see, the change happened, right? This is the yield point. We can see up to 0 to this position, the curve was straight. After that, it is vertical, straight line, horizontal. So this is the yield point. So definite yield point is there in the mild steel. Whereas in the HYSD, that cold deformed worked bar, you won't find any defined yield point. So you can't tell which this curve, if you see which point the yielding started, we don't know. It may be started from here or here. We don't have any defined yield point. Whereas here in this diagram, if you see very clearly, you can tell from this point yielding happened. But in this HYSD bar, it is very difficult to tell. So what IS code said is 0.002 corresponding to that like strain level 0.002, this point, if you see 0.002, so that strain level, if you draw a parallel line with the this line, parallel line we drawn, this dotted line, if you see, and where what location it intersects, that is our basically yield yield point. So yield point corresponding to 0.002 strain level, whatever you get, Fy, wherever it intersects, that you consider it as a yield point. That's our IS code says. Okay, so now these are the very important stress strain diagram of steel you have to understand properly. So this is the typical, actually if you perform in experiment in laboratory, you will find this type of diagram. You will have A is the first yield point, you will have C is the second yield point, then you have alternative strength and fracture will happen. This is the typical diagram if you do it in the experiment in the lab. Whereas our code simplified this diagram into this simplified diagram. They just chopped off this top portion and made it into straight lines. This is the straight line if you see. So this is the mild steel, this is the stress strain curve, whereas for the cold work deformed bar, that is, you will get this type of diagram. Now one more very important part is we have discussed about the safety factor. Okay, so what is safety factor? So concrete, if you see, we did some histogram if you recall. uh, uh, So now we have discussed two materials, right? One is steel, another is concrete. So concrete, if you see, it is made up of in a site, and it is made up of four different materials: coarse aggregate, fine aggregate, cement, and water. So all these four ingredients may have impurities. That's why we have used histogram. If you recall, last lecture we have discussed in details how to calculate the characteristic strength. So we have drawn the histogram and all, and we find it out the characteristic strength. Probabilistic approach we have considered. Whereas steel, if you see, steel is made up in a factory. It is not made up in a site, but in some large factories we made it up, the steel material, rod bars. And much control environment is there. Everything is controlled in a, production of steel. That's why the impurities in a steel is less compared to concrete. That's why the uncertainty of the strength also less in a concrete in a steel compared to concrete. That's why here we are not using an histogram, something like that, because steel is good, because very less impurities you will find in a steel. That's why if you perform multiple steel strength, you will find all will give very similar value, because it is steel is made up in a factory, and all skills labors are working in a controlled environment. It is produced. That's why the steel will have the properties of all the materials steel will have same similar. Whereas concrete is made up in a site, which is the all the four ingredients will have impurities, and in each site also, site to site, it will vary. The skill, labor, and all, everything will be happening. Because of that, the impurities or the strength variation in the concrete will be more compared to steel. That's why we have used the probabilistic approach to identify the characteristic strength. Whereas in a steel, basically we plot this type of stress strain curve, and we divide our Fy, that is yield strength, with a partial safety factor of 1.15. Whereas in a concrete, we divide this with 1.5 as per our limit state IS 456. This is whatever characteristic strength of concrete M20, if you get it. So we won't use for the design purpose, we won't use 20 MPa, the characteristic strength of the concrete. We divide 20 divided by 1.5, and then we use that. So 20 divided by 1.5, we will get something like 15 or so, 15, 16, something. So 15, 16 MPa we will use for our design purpose. Whereas for the steel, the safety factor is 1.15, much less. Okay, so Fy divided by 1.15, for example, this plot is for 250 MPa. So Fy 250, if you see this grade of steel, you will get this type of stress strain curve. So yield point is basically 250. So Fy is yield point 250 Newton per mm square. But for our design purpose, we consider Fy divided by 1.15, which is nothing but 217.39 Newton per mm square. So when we design a structure, we won't consider the strength of the steel is 250. We consider it as a 2.7. So we consider less to become more safer side. So we divide it by 1.15 and we get this value, and this will be our yield strength while considering the design of structures. Similarly, for here also, whatever yield strength you get Fy, we divide it by 1.15 with the partial safety factor, and whatever value you get, that will be our actual that value we'll consider while designing the structure. So this is the properties of steel. Now some other important factors we'll consider for other important factors for considering the materials. One is mixing, that concrete is mixed, right? In that clause you will find what is the properties of mixing. Similarly, formwork also we have to make before casting. So this how to make the formworks and all in this clause number 11 you will get it IS 456. Similarly, assembly of reinforcement. If you see in a site, how they put the reinforcements and all, how to do that you will get it in the clause number 12 IS 456 in that IS code. Similarly, transportation, placing, compaction and curing you will get it clause number 13, all these details. Sampling and strength of designed concrete mix clause number 15. Acceptance criteria clause number 16. Inspection testing clause number 17. So if you go to IS 456 and clause number 10.3, 11, 12, something like that, you will see all these parameters are explained in details. So in the subsequent lectures we'll be using all these criteria and will ultimately design our structures. So basically we have completed the material part. So in a concrete design, we need two materials. One is concrete, another is steel. So concrete properties we have seen in the last lecture where we have discussed the characteristic strength of concrete, which is very important. And then we have seen the flexural strength, creep, and all these shrinkage, all these things we have seen in the last lecture. And in this lecture, we have discussed about the stress strain curve and what is the yield strength of steel and how to calculate it. And why the partial safety factor for steel is 1.15, whereas the partial safety factor for concrete is 1.5, because concrete is made up in a site, and site, so much uncertainties will be there, like unskilled labor may be there, or the material improprieties will be there, whereas steel is made up in a factory, which is much controlled environment you will find, and the labors are also skilled, everything is automated. So that's why the impurities in a steel is less, whereas impurities in a concrete is more. That's why the partial safety factor also we use here for the steel, it is 1.0 1.15, whereas in concrete we use 1.5. So that completes our this lecture. So next lecture we'll discuss about the many design philosophies, like limit state method, working state method, ultimate load method. All these design philosophies we'll discuss in details, and subsequently we'll start our actual design of structure.